In this video, we're going to use residual analysis to check the conditions for inference in a multiple regression context. So notice we're using a different model than we were before. We've got an additional slope, an additional predictor, but the conditions were all written in terms of the residuals. So those conditions are going to be the same. So we've got the same conditions in terms of the residuals, and checking them is basically the same too, but there's a few special tools in JUMP that we're going to need to use. So first we need to have an association between x and y that's linear in the population. And with simple regression, we checked this by looking at a plot that had residuals on the y-axis and the explanatory variable on the x-axis. But now we have more than one explanatory variable that we want to take into account. And so the way we do that is we use the predicted values instead. So these are our y-hat values for each individual in the data set. And the reason that that's a good option is because that depends on both x1 and x2. So it's kind of a way of taking both explanatory variables into account at once. And this residual by predicted plot is going to come out by default when we do analyze fit model. So I'm doing analyze fit model, putting my price as the response, and then I want to look at size and the location as the explanatory. And if I scroll down just a little bit, I can see the residual by predicted plot. This one's pretty easy to read. Sometimes for whatever reason, all the dots are kind of like scrunched up, and it makes it easier if you change the axis. So it has like the minimum and the maximum here, so you can always change those numbers. So if like all your dots are clumped in the middle for some reason, then you can just set your minimum and maximum closer to where your data is, just to spread it out, make it a little bit easier to see. So when we're checking for linearity, we want to see just like this nice cloud of points around the line. This would represent linearity. We don't want to see any curved patterns like this. So unfortunately, I do kind of see a curved pattern. If I trace a line through the residuals, it kind of looks like that. So I am worried about linearity here. I would not say that this is a linear relationship. And we'll talk more about why that might be in a second. The next condition that we always want to think about is whether our data was gathered using randomization and the observations are independent of each other. So this is not one that we can check by plotting the residuals, but it's still really important to check. So there's two types of randomization that we might have. When we're talking about regression, the most common is random selection. So if you have random selection, the purpose of that is that it allows us to generalize to the population. So like if we wanted to make conclusions about this whole area, of whether the size and location have this relationship to price in a whole real estate market, then we would need to know that these houses are representative of that market. So either that they were randomly selected or that we have like demographic information or something to indicate that they were randomly selected. Random assignment is a little bit less common in a regression context because a lot of times we're not randomly assigning these quantitative predictors. Like obviously you can't randomly assign a house to its size. That doesn't really make sense. But if you did have random assignment in a different kind of context, the purpose of that would be to draw cause and effect conclusions. So if you don't have that, then it's possible that you could have some kind of confounder that's actually causing the association between your variables. It may not be a causal relationship. Our third condition is constant variance. So we don't want the spread of the residuals to change based on the explanatory variable. We want this nice, even vertical spread at all points along the axis. So if we get that, that would indicate constant variance. Whereas if we have like a funnel shape like this, where we've got, really close on one end and much more spread out on the other end, then that would represent non-constant variance. So constant variance is a little bit harder to see when we don't have linearity, but just looking at this one, I don't really think constant variance is the problem, because if I kind of try to like trace it, it kind of seems like the vertical spread is pretty much the same all the way along. Obviously it's not a straight line, but I think it looks pretty good in terms of constant variance. So I'm not worried about that one so much. And then the last one is that the residuals are normally distributed. So there's two ways to see this. You can look at a histogram of the residuals, or you can make a QQ plot, also called a normal quantile plot, and check it that way. So unfortunately, we don't get this automatically in the output. We don't see the residuals. It doesn't give us a histogram. And so we're going to have to create our own graphs of that. So if we go up here to the response, there's a little arrow here that allows us to save the columns. I'm going to save the residuals column. So now, going back to my data set, I've just got a new column of residuals where it calculated the residual for every single house in the data set. And now I can analyze that just like I would any other variable. So I'm going to do analyze distribution, and I'm going to pick the residuals. And I like to stack them to see them horizontally. So I can see, you know, it looks pretty good. It's sort of hard to tell the exact shape because we only have 13 houses in this data set. But I don't see any like extreme skew or outliers. There's kind of a little gap here, but that could just be a coincidence because, I mean, we're talking about like 1 or 2 houses in each of these bins. So if I wanted to make the quantile plot, the QQ plot, I can click the arrow next to residuals, and that's one of my options, normal quantile plot. So it looks a little different because they put it on top here, but we're reading it the same way. We're looking to see if these points fall in a straight line. And in this case, you know, they're not perfect, but if we look at these guidelines, they're all well within the guidelines. So I don't have any evidence of non-normality here. I'm not too concerned about that. And there's actually some advantages to saving the residuals on your own because then you have more options for how you explore them. Another thing that you can do is you can save another column for the predicted values. So these are your y hat values. I'm going to do that. So now in my data set, I have both a column of residuals and a column of predicted values. And I can make my own residual plots with these. So I'm just going to go to Graph Builder. And the residual plot we've been using is the predicted values on the x-axis. These are our y hats. And the residuals on the y-axis. So there's that graph we saw earlier with that curve that was making us worried. So to get a little information about why this model isn't fitting, let's try looking at it based on location. So I'm just going to take lake and put that over here for color, just so I can see which are which. And notice that these 2 parts of the line are basically representing the 2 locations. So if I look at the not lakefront houses, those residuals are sloped down, and for the lakefront houses, those residuals are sloped up. So it seems like those 2 locations may actually have different slopes, and our model is not taking that into account, right? Our model is an additive model. It has no interaction term. So at this point, we have not allowed for different slopes. Maybe that's something we should consider. So later on, we'll do a model with interaction, and we'll be able to test and see if that improves the model.